My name is Giuseppe Tinaglia, and I'm a professor at King's College London. In this talk, I'm going to talk about several results regarding the geometry of constant mean curvature surfaces embedded in R3. And these results are joint work with Bill Meeks. Okay, let's do it. Let me begin this talk by describing the objects that we're going to talk about. So we start with the oriented surface M in R3, and if they take the derivative of the unit vector field, we get a map from the tangent space of M to the tangent space of M. And negative of this derivative is called the shape operator, and we denote it by A. What can we say about A? So A is symmetric. The eigenvalues are called the principal curvatures of M. And the Gauss curvature is the determinant of A, that is the product of the principal curvatures. The mean curvature is half the trace of A, and the square root of the sum of the squares of the principal curvature is the norm of the shape operator, or also norm of the second fundamental form. All these quantities, Gauss curvature, mean curvature, and norm of the second fundamental form, are related by the Gauss equation. So what does the mean curvature say about the surface M? Okay, if we take a smooth normal variation of M that fixes the boundary, so this is going to depend on a function phi, which is in C0 infinity of M. So then we construct this one parameter family MT phi in this way. Okay, then the area of MT phi is an honest function of one variable. And when we take ddt of the area at t equals 0, we get -2 integral of M h phi. Okay? So with this in mind, we define a minimal surface as critical points for the area functional, which means that this derivative has to be 0 for all phi's in C0 infinity M. And this is the same as saying that the mean curvature is identically 0. M is a constant mean curvature surface, or CMC surface, if it is a critical point for the area functional under variations which are set to preserve the volume. So we're adding this extra condition on the phi's. Okay? And from the first variation formula, it is clear that this is equivalent as asking that the mean curvature is constant. So examples of minimal surfaces are, of course, the flat plane. Then another example is the catenoid, which together with the plane is the only minimal surface of revolution. And the catenoid topologically is a cylinder, so it has genus 0. Another important example is the helicoid. And the helicoid, together with the plane, is the only ruled minimal surface. And the helicoid is topologically a plane, and therefore it also has genus 0. Then, if we talk about non-zero CMC surfaces, okay, clearly minimal surfaces are examples of constant mean curvature surfaces with mean curvature equals 0. We're talking about non-zero CMC surfaces. Then, of course, there is the plane, there is the sphere, there is the cylinder, and this can be thought as part of a larger family of CMC surfaces called Delaunay surfaces. And these are all surfaces, when you fix the non-zero mean curvature, the linear surfaces are all surfaces of revolution with that constant mean curvature, okay? And so if you fix the mean curvature, say to be h equals 1, then there is actually a one-parameter family of surfaces. And for certain values of the parameter, you get a cylinder. And for another value of the parameter, you get a chain of spheres. This necks connecting these things that look more and more like spheres pinch off, and these are in fact spheres in the limit. When we have a surface which is given as a graph of a function, we can write this geometric quantities using nice partial differential equations. So here's the equation for the Gaussian curvature. Here's the equation for the mean curvature, which is the prototypical example of a quasi-linear elliptic PDE. And also when we have that the surface is given by the graph of a function, then we have this estimate for the norm of A, which tells us that if you know that the gradient is bounded, so not only you have a graph, but also you know that the gradient is bounded, then the norm of A and the norm of the Hessian are more or less the same thing. And it is, among other things, the fact that you have this nice PDE tells us that minima and CMC surfaces satisfy some nice properties. So a property that it's going to be important in this talk is the so-called one-sided maximum principle. And so let me begin by saying that the mean curvature depends on the orientation, because it's the trace divided by 2 of minus dig c, okay? But what doesn't depend on the orientation is the mean curvature vector. So you take h times c, okay? And now, so let's say you have, you're able to say that you're dealing with CMC graphs with bounded gradient, okay? And you're dealing with these graphs, and they're getting closer to each other, but they are disjoint. So what could happen? Okay, as it turns out, what could happen can easily be summarized by what happens in the case of spherical caps. If you have two spherical caps getting closer to each other, then if the mean curvature vectors are pointing in opposite directions, then you can get them as close as you want, and eventually they touch at one point. So they'll touch, but the geometry, so that you know that at this point the mean curvature are pointing in exactly the opposite direction. If the mean curvature vectors are pointing in the same direction, like in this picture in the middle, then you can get as close, you can get these two pieces as close as you want. But eventually, as soon as they touch at one point, they actually touch everywhere, and they become the same spherical cap. Okay. On the other hand, finally, in the third picture, if the mean curvature vectors are pointing against each other, then you can't get the north pole of this spherical cap as close as you want to the south pole of this spherical cap without the two spherical caps intersecting. Okay, so there is a neighborhood here of this top spherical cap where this bottom spherical cap cannot come into unless you intersect the surface. Notice that in the minimal case, you could do the same in the minimal case by thinking about flat planes. All that could happen is this picture in the middle. Two planes, if they're parallel, they can get as close to each other as we want. Eventually, when they touch, they just become just one plane. Okay, but this happens for CMC surfaces. This happens only for non-zero CMC surfaces. This happens only on one side, so that's why the one-sided maximum principle. Okay, let me briefly talk about the classification of complete simply connected surfaces embedded in R3 with constant mean curvature. So what can we say in the compact case? The compact case, if M is a closed, that means compact without boundary CMC surface in R3. So we know that M cannot be minimal because a minimal surface, because for a minimal surface, the Gaussian curvature is never positive, but if it's compact without boundary, we know that there is always a point where the Gaussian curvature is strictly positive. Now, if M is genus 0, so we're not assuming actually both of the hypotheses simply connected and embedded right now. It's sufficient to have genus 0, and then this is a round sphere by a result of half. And if M is embedded, but not necessarily genus 0, then it was proven to be a round sphere by Alexandrov. Okay, so these two classifications of the round sphere are, very similar in flavor. I mean, they're both classifications of the round sphere, but in fact, the proofs are very different. Okay, and so are there other examples? So what happens if you, are there examples of closed compact CMC surface in R3 which are not the round sphere? It turns out that it took quite some time to answer this question, and in 1984 Wente constructed the first example of CMC surface in R3, which is different from of closed CMC surface in R3, which is different from the round sphere. So it cannot, this is called the Wente torus, and it cannot be embedded because of half, because of Alexandrov's result, and it cannot be genus 0 because of half result. Okay, so this, after this example, actually there are many more examples. Started with Capuleyas in 1994, and then Mazel-Picard, Pollack, many examples now. Okay, so this kind of takes care of the compact case. So what can we say about the non-compact case? When H is equal to 0, there is this classification results due to Coulomb inequality and Meeks and Rosenberg, that the plane and the helicoid are the only complete simply connected minimal surfaces embedded in R3. Okay, and notice that you need both hypotheses here, simply connected and embedded. If you're not simply connected, you could get the catenoid, for instance. And if you are not embedded, you could, for instance, take the universal cover of the catenoid. Okay, but with this hypothesis, then you only have two ways of embedding something which is topologically a plane in R3, either a minimal and with mean curvature 0. Either it's a flat plane or it is the helicoid. So then we can ask the same question about non-zero constant mean curvature surfaces. And the question is the round sphere the only complete, simply connected surface embedded in R3 with non-zero constant mean curvature? And the answer is yes. And this is a result that I proved with Bill Meeks. You can ask the question a different way. You can say, can you embed a complete, simply connected surface in R3 with non-zero constant mean curvature and get something which is different from the round sphere? And if you ask this question in this way, then the answer is no. The round sphere is the only thing that you get. So in the minimal case, you have the plane and the catenoids. In the CMC case, you only have round spheres. So this our result, together with Kolde-Minkowski and Meeks and Rosenberg result, classify simply connected CMC surfaces embedded in R3. They can only be planes, helicoids, or round spheres. So this result actually was the final, it was the headline result of a deeper analysis of the geometry of CMC surfaces. So I'm going to talk a little bit about this analysis, and in order to do that, let me introduce a definition. So we're gonna fix the mean curvature to be 1 because by scaling we can get any non-zero value of the mean curvature. So whatever I say related to constant mean curvature 1 has an analogous result for H non-zero. And I'm going to call it one disk, a simply connected surface embedded in R3 with constant mean curvature 1. So the results that we have with Bill is the following, that the radius of a one disk is bounded from above. Okay, independent, of course, so it only depends, so it doesn't depend on n, this bound. Okay, and therefore with this result, it's fairly easy to classify the round sphere, because the radius estimate implies that if you have something which is complete, then it is compact, and then it is an embedded sphere because it's simply connected and it's embedded. And then once you get to this point, you can use your favorite theorem, either Hoff or Alexandrov, to say that it's in fact a round sphere. So the radius estimate itself is a consequence of the following intrinsic curvature estimate. So this says that if you are on a one disk and you stay away from the boundary, the second fundamental form is bounded by a universal constant. So by a constant which depends on the mean curvature and the distance to the boundary. This result is actually very hard to prove, so I'm not going to go into the proof of this result, but I'm going to say a few words about the significance of bounding the norm of the second fundamental form. So we know that in general, if you have a point on a surface, we can always find a small neighborhood of the point where the surface is graphed over its graphical over its tangent plane. But the size of this point the size of this neighborhood depends on the point, okay? And it so happens that if the second fundamental form is bounded, then you don't have that. So here's the computation that tells you that if you have a point in the geodesic ball of radius r centered at P, the distance between the two normals is bounded by r over c. And for instance, if you take an r a uniform R such that R over C is less than pi over 10, then this estimate gives you that it's locally a graph. Okay, and in fact, if you look at what C is and the fact that you have this estimate that I talked about before, you have some C2 estimates for this graph where this C might be a different C. Maybe this is not a 10, maybe this is 1,000. I haven't done the calculation carefully myself, but I mean, you have some uniform estimate that depend on C. Okay, and notice that up to this bullet, we haven't even used the fact that the mean curvature is constant. Okay, then we use Schauder's theory and the fact that U satisfies this partial differential equation and H is constant to go from uniform C2 estimate to uniform C2 alpha estimate. Okay, so if you are a CMC surface which has bound the second fundamental form, then locally but uniformly you have this property that you're locally a graph with C2 alpha estimates. So for instance, what can you say? Suppose that you have a sequence now. In this case, you have a sequence Mn of minimal surfaces. Okay, let's take minimal surfaces. And the second fundamental form is bounded uniformly. Then we have that nearby. Actually, let me state the results first. So we have a nice compactness result that if you have a sequence of minimal surfaces properly embedded in U, and there are two things. First, the second fundamental form is uniformly bounded, and then the second fundamental, the area is also uniformly bounded. Although good things happen even when this is not true. You just have to talk about laminations. Okay, but anyway, if you have these two properties, then a subsequence converges to a minimal surface M, which is properly embedded in U. Okay, and an analogous result is true for H surfaces, but you don't have embeddedness because you have you can have the picture of the two spheres. I mean, not necessarily two spheres, but of two CMC surfaces touching in the limit, like in the case of these two spherical caps that I talked about before. Okay, so how do we go about proving this? Okay, so if P is a point is an accumulation point for this the sequence of surfaces, then you have graphs with C2 alpha norm uniformly bounded, but then you can use Arzela-Ascoli to obtain a subsequence converge C2 to a minimal surface. Okay, if you don't have minimal, then you have bounded in C2, so you can still say something, but you don't have C2 convergence if you have a C2 bound. And we like C2 convergence because all of the quantities that we care about, Gaussian curvature, mean curvature, they, in second fundamental form, they depend on two derivatives. So for instance, that's why we know that the limit is a minimal graph because of the convergence in C2. Okay, and then a prolongation argument, kind of like once you start, then you use a prolongation argument to get a whole surface. You attach. Eventually, you take a, once you get one graph, you look at a point in the boundary of this graph. That's also the limit of points in the sequence. You attach another graph and keep going. So another thing about this curvature estimate is that this curvature estimates while our work was inspired by Kolde-Minkowski theory, which was done for minimal disks. This curvature estimate fails in the minimal case. Counterexamples are the helicoid. If you scale a helicoid, it's still a minimal surface, and the second fundamental form blows up on the vertical axis, okay? And a sequence of scaled helicoids converges to a foliation of our three biparallel planes, and there is a vertical line. If these are vertical helicoids, there is a vertical line which are singular points of convergence where the second fundamental form blows up. Okay, so basically what we call the Minkowski analyze the geometry of minimal disks around the point with large norm of A, and they prove that the geometry looks like that of a helicoid. And we analyze the geometry of CMC disks, non-zero CMC disks around the point with large norm of A, and we prove that there are no such points. Okay, so I'm gonna give you a few seconds to read the definition of the injectivity radius. Okay, and so first let us observe that if the second fundamental form of a surface is bounded, then the injectivity radius is bounded from below, because we have already a nice description when this happens with everything is locally graphed, but uniformly locally graphed, so on and so forth. Okay, so Meeks and I proved that if M is a complete connected H surface with H bigger than 0, then having bounded normal second form is equivalent to having injectivity radius bounded from below. Okay, one equivalence is fairly standard, so our work was in the other direction, and it follows because when you have injectivity radius bounded from below, then small geodesic balls are disks, and then you can apply our curvature estimate for H disks. Okay, with this in mind, I want to talk about this result. An area estimate for CMC for non-zero CMC surfaces embedded in the flat 3 torus. Okay, so this is the theorem. And notice that this theorem fails in the minimal case because of examples constructed by Trezé. And here are some examples of non-zero CMC surface or H surfaces in the 3 torus. Okay, so we prove this theorem by contradiction. Let's assume that Mn is a sequence of compact H surfaces with a fixed genus and area becoming arbitrarily large. Okay, one thing to notice is that Mn separate T3, the torus, into 2 components, one of which is mean convex. This is going to be important to apply to do techniques that involve solving plateau problem, for instance. Okay, the first claim is that we have to have the injectivity radius going to 0. Okay, so arguing by contradiction, suppose that that's not the case, that the injectivity radius is bounded from below. Then we can apply our curvature estimates to say that the second fundamental form are bounded from above. Okay, but if that's the case, then everything looks graphical, and we can apply the properties of non-zero CMC surfaces where everything looks graphical, in particular the one-sided regular neighborhood. So the pieces of the surface cannot come close to each other on one side. Okay, not only that, but if the second fundamental form, so that means that you have an embedded regular neighborhood on the mean convex side of this Mn. Okay, and notice that here also the fact that Mn separates the torus comes into play. Okay, so this means that the picture that was in the middle of the slide where we're talking about properties of graphs, the picture where you have two spherical caps becoming one spherical cap, that cannot happen because of separation properties. Okay, so not only you have this regular neighborhood, but there is a relationship between the area and the volume of this regular neighborhood. But now the volume of the regular neighborhood can be bounded by the volume of T3, and therefore you get a contradiction when n is large. Okay, because the right-hand side of this inequality is fixed. Okay, so by the results, the previous results that I mentioned with Mill-Meeks, if so if the injectivity radius goes to 0, okay, let me restart. So let me introduce this definition. Okay, we call singular points where the norm or second fundamental form blows up. Okay, and the previous result gives us that the injectivity rate. So we have that if you have a point where the second fundamental form blows up, then the injectivity radius has to go to 0 by the estimates, by the previously mentioned estimates for the normal second fundamental form. Okay, so let's pass to a subsequence, and let's assume that the set of singular points is a relatively close subset of the torus, and we have already shown that this delta is non-empty. Okay, in fact, we can also fairly easily show that delta does not consist of a finite number of points. So arguing by contradiction, suppose it does. Notice that we have this property, again, by the one-sided regular neighborhood, that if you take a compact set, in this case, it will be finitely many points, and you take the area of a man intersected with this compact set. Sorry. If you take a compact set of T3 minus delta, then you have here bound the second fundamental form, because the delta is the set where the second fundamental form blows up. And in this compact set, you have area estimates because of the one-sided regular neighborhood. Okay, we're going to use this property to prove that delta does not consist of a finite number of points. And the proof is fairly standard. So if we take T3 and remove, some small balls around the singular points where delta is just going to be small, just depending on the mean curvature, then the area is bounded. Okay. But by the monotonicity formula, the area inside the ball can be bounded by the area outside the ball. Okay, and then the area outside the ball can be bounded by, again, the area of the whole of this whole thing. Okay, and therefore we have that the area is bounded by the number of singular points times this fixed constant, and this gives a contradiction because m is finite and this constant is fixed. Okay, so the interesting case is to prove that the number of singular points does not go to infinity. Okay, so this is a we already proven that does not consist of a finite number of points. Now we're going to prove that it must consist of a finite number of points, and these two things will contradict each other. Okay. Again, blow-up points means injective radius goes to 0. What can we say about the geometry of the surface nearby 0? So in order to study this surface, we're gonna study these limits. We're gonna scale by the inverse of the injective radius. Okay, and so this is actually not exactly what you do. I'm not gonna talk about the exact scaling, but I'm gonna leave it in the slides, so feel free to check it out. But suppose we can actually do this. What can we say about the scaled surfaces? Well, the injective radius at 0 is 1, and now the mean curvature are going to 0. Okay, so we say that, so we claim that sigma n converges to a catenoid or to a complete properly embedded minimal surface of positive genus. There are two cases to consider. Either sigma n has uniformly bounded norm of A, so there are actually, when you scale, there's no blow-up points, or sigma n does not have uniformly bounded norm of A. Let's do the first case first. In the first case, then, again, we can, when this is bounded, again, we have nice compactness results that I already talked about. And then we can use the classification of complete properly embedded minimal surfaces of finite genus to say the following. Okay, the sigma n converts to a complete properly embedded minimal surface of finite genus, and that there can be either a flat plane or a helicoid. When the genus is 0, you have these 3 bullets: a flat plane or a helicoid, a catenoid, or a Riemann minimal example. Else, it's a surface with positive genus. And we don't mind too much about this bullet because the genus is an additive quantity, and so you cannot have too many points where this appears. Okay. Okay, so already we can rule out the plane or a helicoid because the injective radius at 0 is 1 in the limit. Okay. And so see, here's a picture of the Riemann minimal example, which is a stack of planes connected by catenoids. So before I rule out the Riemann minimal example, what happens in the case 2 is case 2 does not have uniformly bounded A, then sigma n converges to a so-called parking garage structure, so which is kind of like 2 helicoids connected in this way. Okay. So far we have that the limit is either catenoid or a surface with positive genus, a Riemann minimal example, a parking garage structure. So we need to rule out the last 2 bullets in order to prove our claim. So let's rule out, so I'm going to rule out the case of a Riemann minimal example, and the way to rule out the parking garage structure is more or less the same. Okay, so let's take a curve like this on our Riemann minimal example, and we first claim that this curve is not homotopically trivial in Mn. It doesn't bound the disk. Well, recall that Mn separates T3 into 2 components, one of which is mean convex. We can solve Plateau problem then and find a minimal surface that is bounded by this curve, but you know this curve does not bound the disk in the small ball where this Riemann minimal example appears. So the minimal disk has to leave the ball, but that contradicts the convex hull property for minimal surfaces. Okay, so then we prove that these two curves cannot bound an annulus. Here, the arguments are similar, but not exactly the same arguments, because so here again, you solve plateau problem, you can't bound a minimal annulus in the small ball, so this annulus has to leave the ball. But that's not necessarily that were a contradiction. If this was, that would contradict the convex hull property if this was in R3, but that doesn't contradict the convex hull property in the torus. And so the argument is a bit more complicated. We have to lift this annulus into R3 and obtain a contradiction by studying the geometry of this annulus. Okay. So, well, it turns out this is a fairly straightforward topological fact that if you take a surface which has fixed genus and you take a sufficiently large number of curves which are not homotopically trivial and are pairwise disjoint, then eventually there would be a pair that bounds an annulus. But in this case, this picture, this is like the number of curves, the number of pair of curves which are not homotopically trivial is becoming increasingly large, but the genus is bounded uniformly. So eventually, we will get a pair which bound an annulus, and we obtain a contradiction. Okay, and again, more or less the same argument can be said when we have the appearance of a parking garage structure. Okay, so we do have the sigma n converge to a catenoid or to a properly embedded minimal surface of positive genus. Again, we are trying to prove that the number of singular points is finite, and since the genus is additive, we don't care about the points when you get positive genus. You just only get it a finite number of times, which is bounded by the genus. So what we want to bound is the number of catenoids. Okay. Okay. So now, so we've picked P a blow-up points, and suppose there is a sequence of. So suppose that this is a blow-up points where the catenoid appears, so that there is a sequence of closed loops which converge to the closed geodesic of the catenoid forming a P. Okay, you can use a flux argument to prove that gamma n P actually cannot bound a disk. It's not homotopically trivial in Mn because the flux is homologically invariant. So if the flux, if it were bounding a disk, then it would be 0, but the flux on a catenoid is not 0. Okay, so we want to prove that if you have 2 points, 2 blow-up points, and the related loops bound an annulus, which eventually will be true because the genus is bounded if you get more and more catenoids, then the number of such annuli is bounded. Okay, and this again it's an argument that involves the Alexander reflection principle. The first step is to lift this annulus to R3, and one can prove that this annulus is large in a sense that it occupies a decent amount of volume. Okay, in fact, so and then you can prove that when you go back to T3, again, it occupies a decent amount of volume in T3, and this amount of volume does not depend on the blow-up points. Okay, but then so each time you create an annulus, you create volume, but the volume of T3 is finite, so you can't have too many annuli of this type. Okay, but in fact, okay, so now the conclusion. So now there is, if there is an infinite number of points where the block points where you get a catenoid, then these are not homotopically trivial. Eventually, you get an arbitrarily large number of curves bounding annuli, and this contradicts the fact that the number of such annuli is bounded. Okay, so this finishes the proof of the area estimate. Okay, and so just wanted to point out that what we just proved is not an area estimate, but actually we proved a compactness theorem for H surfaces in a torus. So if you have so let me give you some time to read the definition of strongly Alexandrov embedded. So we have this theorem that if Mn is a sequence of compact H surfaces in T3, H bigger than 0 of genus at most G, then up to a subsequence it converges to a non-empty, possibly disconnected, strongly Alexandrov embedded surface M infinity of constant mean curvature H and genus at most H. And the convergence is moved away from a finite set of points delta. And the set delta is a subset of the set of points where M infinity is not embedded. Okay, and so the idea, why do we have this result, is because in the previous argument, actually, to bound the number of singular points, we did not use that the area was going to infinity. Right? You can prove that once you have the sequence, you have the number of singular points is bounded, and then you can remove the singularities by using the area estimates and bounded genus. And then density arguments, you can show that delta is in fact a subset of points where M infinity is not embedded. And also density arguments show that the singular points can only be at the non-singular points. And this finishes my talk. Thank you very much.